So what safety critical system does, it actually is intended to what the system, what it does is it's intended to achieve its own level of safety integrity. So like we have to implement certain safety functions. So when I say I work on flight control system, so the controlling of flights. So I control the pilot controls the landing gear, or he navigates, he sees a navigation panel to look at when he is flying the plane. All these are all safety critical, because without the navigation panel functioning, he cannot go to the desired destination. So these are all the systems. So anything that we work around on these applications are critical, safety critical, because if he stop seeing the navigation panel with the right display, he would misses the destination points. I mean, so it goes as a flight waypoints. So when a pilot is flying, he flies with the waypoints as his. So you would have seen, like in GPS, how you could track a location. So it's the same way. So there's something called coordinates which he follows. So based on those coordinates, he will move to his destination. So all these systems that give the flight attendant, or the flight pilots, or the first officer, um, that gives him a navigation point or a view, or the different pages view, or the alert zones. All these systems are all embedded in the flight. So in avionics, it's embedded in the flight controls. So if whatever you see, there is something called a multifunction display, which is the primary display that any pilot would see. So we work on all these systems. So these are all considered safety critical systems. So what is an objective of safety critical system? So basically, the safety critical system addresses like customer gives us the system specification, right? So the safety requirements are like they address all the system specification given by the customer. The customer says, okay, I need this kind of light which gives me the navigation display, the cockpit display, which has the several pages, which shows me the wings, which shows me the entire area around the flight. So all these has to be seen by the pilot. So the customer gives us a specification saying that I need a system which embeds all these, and we actually try to figure out what are the safety critical requirements in those. So we split. We find out. We get the entire set of requirements from the customer and find out what are safety requirements, and that is what is given more importance when we start the development of those. Of such a software. And then what is important on that? So once you have implemented, your quality of the software should be assessed. So that is where you do the verification and validation to assess the quality of the software. Then what is essential? The software design description, which has to be right. So in the very initial stage, the design of the software should be well defined. So it should be covering all the system specifications along with the derived software. So if you have been given a navigation display, what all you take out the system description and then derive it to a software. You say that, okay, in the navigation display, what I have, these are the features I need to add in. You can have your own features, and you can have the features based on the system specification. So all this has to be well defined in a software design. So that is that is what is done in a software design description. Then we have the certification and approval. So once you have all this defined, the quality process assessed and all that, then you have the certification and approval that it has to go through. So only when those certifications are achieved with few guidelines. So I believe you would have heard about standards. So every industry has its own standards. Like you have the IEEE standard for the engineering aspects. So we have certain standards on each of these industries, like avionics and locomotive. Everything has different standards, and the primary objective of those standards is to take care of the safety objective. Okay, and there is something called extensive. Okay, then there is some in the safety critical system. It's very important. Testing plays a very important role because implementing would it does take a high cost. It does take a huge cost, but and even more time. But testing it and finding out whether the software is really meeting the system specifications and meeting the standards, that is done by extensive testing. So this is very essential phase in a safety critical software development or the safety critical environment. So we do if you say, when you say extensive software development testing, it's about the functional and code coverage. So you verify whether the functionality works as per the expectations on the system of the system, and whether the code has achieved all those specifications, and have you covered all the functionalities. So this is what is done with extensive testing in while in development. So we do that. We call it as unit testing, or we do the unit testing and all the functional testing or module level testing on the software development phase. Once the development is done, we do an extensive integration testing. So that is once you bring in the whole system with the hardware, software, they all are merged together. You integrate all of them together, and then there is a certain aspects of the software, hardware, communication, the links, whether they are linked properly. All these are being tested in the integration phase. So that also goes through a rigorous testing. So safety objectives are primarily these, where you have to make sure that these are done, and then only you can give out a best system, a best software for that embedded system. And of course, we have to give a complete documentation of what we have done. So what when you have safety when you say that the system is safety critical, you should also foresee risk. So what are the different sort of risk that you can foresee in when you say that it's safety critical? Then you have to assess what kind of risk is possible. So when you say what is that severity of the risk that you could face? So one is catastrophic. That is the highest or the most severe risk is called as the catastrophic, which could cause death, which is more than 10. Obviously, when in an aircraft you would have more than 100 passengers. It might be a threat if a system fails and the flight abruptly crashes. It does cause loss of lives. So that is catastrophic. Then we have critical, which could cause, I mean, it is not toward a level of crashing and causing death of lives, like death, but it could cause injuries. So those are critical. And then there is marginal, which is like a severe injury. It could be a burn or a severe injury, a bone fracture or something. So those are marginal. And insignificant is just a minor injury, which could be just a minor scratch. If it is in the runway, it could be a minor scratch. So these are the severity levels that we need to assess. So we assess when we say that we are going to work on a safety critical system, we assess the safety requirements, and we assess the severity. What if this system fails? What are the severity? So those are all assessed here. How frequently those aspects can occur. So those things measure in the frequency. So it could be very frequent, that occurs every year. So all these assessments are made when we do the risk analysis. So what we do after the risk analysis is done, what we do is we define a tolerance. So there is something called for each level. So we say that the catastrophic is the most severe level. So here, if you see still 4, that is considered as the most severe level. Still is nothing but safety integrity level. So what happens is when it's most severe, you define a limit. So when within to this, that limit is considered as your severity tolerance. So within that limit, if that requirement, or if that system fails in that within that limit, it is considered as SIL4. The next level is the critical level, which is less than the catastrophic level. So that way, all this safety integrity levels are defined with a tolerable hazard rate. So what used to be embedded system in the past? So this, if you know, I'm not sure if you know the Apollo guidance computer. That was the first modern embedded system, which was developed by Charles Stark Draper, and he did it for the MIT Instrumentation Laboratory. So what he considered that the Apollo guidance computer is risky. Why? Because it had so many monolithic integrated circuits, which are reduced in in size and weight, but it could cause a shortage. So because it's an integrated circuit, any short on any of the circuit, if any failure happens, it's very critical that the entire system crashes. So he defined, when he brought up the system itself, he said that I consider this as riskiest. Then came this Autonetics T17 guidance computer, which was also considered a mass, that was much more bigger embedded system, which had the big microcontrollers. The previous one was just small integrated circuits interconnected with each other, and communicating with each other and bringing up a system which was like a display or a guideline system for the healthcare. But this one, Autonetics, was like a mass system, which was much more critical because it was used in military support for military missiles. So it was to support the military missile guidance. So the targets, they used to give targets through that system, and the system used to point out the targets and like giving points, showing as waypoints, or the target point. They call it at a target point. So they used to give the points of where the targets are, and the missiles used to be shooted on those targets. So this guidance was given by these Autonetics D17 guidance computer. Then I was talking about certification. So when we develop a critical software, we have to ensure that the safety is assessed, the safety of the system is assessed, and we verify it to be certified. Only then it is consumed in the market. It's sold to the market. Only when it is certified, they buy. Even if it is the case, even with an airplane. So only if the airplane is certified, it gets into the market. So these are the different standards we have in each industry. So for the nuclear safety, we have IEEE 880. So we follow these guidelines when we prepare from the software description, design description till the testing. We follow these guidelines, the guidelines defined in these standards. So only when these guidelines are met, we consider that this software system that we have developed is certified to go to the consumer market. So MISRA is something used in automobile industry. Then we have IEC 61508, which is what I'm working on, which is on the locomotive industry. So we use the programmable electronic in the locomotive industry, which is in the trains. So what you see in metro, like many of the things are automated. Right now in the metro, doors open automatically. Everything is done by a programmable electronic. And we had followed the IEEE 61508 standard to develop those systems. Then we have the RTCA DO 178B, which is the airborne system safety, especially for avionics. So what is the present? So these are right now, the development of safety critical system has come to this level where we have the entire navigation system embedded. So if you see, this is a picture of a flight deck, of an aircraft deck. Then we have the GPS service. This helps the captain and the pilot to navigate to the desired destination. So what you see in that meter is just like how you see in an automobile, but there is a different sort of measures like metrics that is followed in the GPS services for aircraft. So what we give here is called flight points. Like we say coordinates, there we call it as flight coordinates, flight points. So all these are seen in these systems. Then we have in automobile, we have embedded this electronic microcontroller, even this anti-lock braking system. This is also an embedded system that has been introduced in automobile industry. Then the electronic stability control, mainly for the steering control. See, I believe that whoever is driving an automobile would know about cruise technology and all this. So this is all embedded. It's all brought with these technologies combined. So it's all done with this set of a small. If you can't believe this electronic microcontroller does a lot, even if it looks like a very small chip. That the interconnection of these microcontrollers brings us so much of technologies that we are using right now. So yeah, so that's what is on the automobile industry. Then we have in the medical industry, you might have seen the vital monitoring system. They are also embedded. Then we have the electronic stethoscope. I believe you would have seen in some hospitals, they have these electronic ones rather than the manual. Then this is a topic I think you would have in your subject as well, the software development life cycle. So I believe many of you know the models, different models. Do you know, can someone talk about the different software models? Any computer science engineer? Hello? No one is willing to talk?
I think everybody are waiting for the QA session.
Okay, okay. No, the thing is, like, this is something that you would have covered in your syllabus. I mean, it should be a part of your curriculum. So, you know, the traditional waterfall model and all that. I believe you would have read that. But what we follow here in our critical embedded systems is this V model. It imbibes everything. It consists of this waterfall model. Right now we are working on a hybrid agile model. I don't know, I'm not sure if everyone is aware about agile. Agile is something that is considered as it helps in continuous integration. So earlier, in the traditional model, which is waterfall, we used to go step by step. Okay, first we get the system requirements, we derive it down to software requirements, then we do the design, then we do the coding, then we do the testing. So it was all one by one. It was sequential. But right now, it's like we are adapting to a new technology, which is what happened in the previous model was it used to take a lot of time because every phase takes its own sweet time to get completed, and by the time we end the testing phase and we are about to get into certification, that is when we get to know that there are so many system requirements or the software functionalities are not working as per the system expectations. So then you go back and correct it, and again you go through the same sequence, which was very time consuming. That is the reason they brought in agile. So right now we are all moving on to agile, where we do a continuous testing. So when the analysis starts, that time itself we start, like when like what I showed you in the beginning. The safety requirements were all assessed in the beginning itself, so that you know what are the safety constraints that you have to take care while developing the software. So all these are done parallelly, one on one. We don't have to wait until the end to get it tested and qualify it as a working software. So that's what we had followed. So this is I think this diagram is pretty much known to all of you. Like what we follow a V model. So from the system analysis, then we have the design, which is called the high level design. Then we derive it down to the software requirements. We allocate each model or each functionality to each subsystem. So when I say subsystem, so when you say there is flight control system, it is a whole system, but it has several other subsystems in it. So what are those subsystems? We call it as, so in the flight control system, we have a navigation system, we have a primary flight display system, we have a multifunctional display system, we have so many subsystems in an entire system. So these are all derived in the software requirements phases. So we split it down to those requirements, and then we bring it down to design. What happens is we have a preliminary design review that's called the software PDR. So once you have defined a design based on the requirements, software requirements, you have defined a high level, low level design, you go through preliminary design review. So you get it qualified from a certified professional who says that, yeah, okay, your design looks almost, it meets our expectations, it's as per the system specifications. So yeah, you can go ahead. So when you get a go ahead on the PDR, we then go to the CDR. CDR is nothing but critical design review. So all this phases we go through, and then we get into, after the design is finalized, we get into software implementation. Right now, we are in a phase where we sometimes get into reverse engineering as well, because when we do coding, until coding, some aspects of the design wouldn't have been identified or wouldn't be clear. So right now, some people are doing reverse engineering, wherein you find that the system merging or this particular interconnection or functionality cannot be mapped together. So when we find such an issue, what we do is we go back to the design and correct the design according to the code. That is something called reverse engineering, which is not advisable, because for this system, for safety critical system, it's very risky. So we would have already done enough risk. That's the main importance of this system, where it has to be very well assessed in the very beginning. So uh, that's the point. So when we say reverse engineering, it's not a very advisable method to follow. Then we have, once you have coded, you do a unit test. The developer himself does the unit test, whether his code meets all the functionalities as per the software requirements that he does. Then we have a low level RBT. RBT is nothing but requirement based testing. So when we give it to the tester, we give him the requirements, we give him the design. We don't tell him the code. And basically the tester shouldn't look at the code as well. So he just has to go see the requirement. If he wants to understand more on the system, he can go to the design and see, but he shouldn't be worried about the code. His main job, because he shouldn't get biased with the code. So the main job for him is he has to test, he has to manipulate few inputs to that software which is developed and give the right set of inputs and trigger the input, the process with that input, and then get the desired output. So if he doesn't get the desired output, he can always reject the functionality as a failure. So all these phases then come in the testing, that is the verification part. So that's where we go to the software, hardware. Once he does the low level RBT, which is the requirement based test, then he gives it to the software hardware integration tester. So what they do is, after the complete set of subsystems are combined to one system, this integration test happens, and then we have the high level RBT and final system, which is the system test bench. Right now we work on simulator benches. So the system integration bench would be there where you can, they wouldn't know about the internal software. They just worry about the system requirements and see whether the requirements are met. Once all these phases are crossed, then we certify it as a good software. So these are the phases of every software. So these are the different engineering phases we split as. So when we say the systems part all comes as systems engineering, the combination, the deriving phase of systems to software is called as software systems engineering, and then we have the phase which is the code called as software engineering. I know these are all part of your curriculum. So then we have capability maturity model integration, which is nothing but assessing the capability of the software. So we have different levels of this capability. So when you go, if you see level 1, which is the initial level, am I going fast, or is there any difficulty in following me? Just let me know. If you want, I can go a bit slower. Okay.
It's fine, ma'am.
Yeah, thank you. So when we talk about this capability assessment, what we do here, we actually start assessing the level of software. Like in the initial level, what is assessed, what is assessed. So whether the processes are working fine, are they reacting to the inputs that we trigger, all these kind of states. So in the initial level, what we do is we have a set of processes, well-defined processes and all that. So we try to see if there is any impact or any failure foreseen when you trigger a particular input. So we try to predict if any such things can happen, if there is a process failure, or if there is going to be a some sort of what is it, some sort of impact on the future undertaking. So all that are assessed in the level 1, which is initial level. And then we go to the repeatable level, where we see whether it's characterized well. So the policies are well defined. The organization, once the policies are well defined, you repeat the same process. So you don't have to again create from the beginning. So that is a repeatable sort of capability. So you say that, okay, this software is capable enough to be used as a legacy in some other project. So that sort of repeatable or reuse technology should also be imposed onto that software. So then you are of level 2. So this is like you qualify yourself to each levels. So you have a defined level, then you have a managed level. These are all like, if you go in depth, it's a separate topic. So CMMI is something, when we say that we are CMMI certified, we either the bare minimum should be level 3, and level 5 is the most optimized. So we only talk about enhancements, and we only talk about improvements. So we right now, most of us in the industries that I've worked on were CMMI level 5 certified. So we are working on to improvements. We are bringing in new technologies, new enhancements and stuff like that. So all the below levels are just the basic. So coming up to the level 5 is considered as the most capable system that we build. So the capability assessment is done over this embedded system as well. Right now, in the current situation, what we see, what are the certain issues that we see in the industries? In aerospace industry, what we see is the air traffic control. You would have seen a recent crash. I'm not sure about that happened. It's not recent. It's a couple of years that there was a uh, failure on the air traffic display. I mean, the flight attendant couldn't, the pilot couldn't see the traffic signals, and he wasn't getting a receipt from the regarding the traffic in the while on air, and he wasn't sure about whether he was flying to the right destination because he was not seeing anything in his screen. So that caused in an abrupt landing. It couldn't. It. I wouldn't say he went and crashed. He went and landed in an unknown area. So those kind of failures are the current system issues which we are working on. People are trying to bring in technologies where we avoid such failures, air traffic control. Then, if you want to see on a day-to-day basis, even credit card authorization denial is a common failure in an embedded system. What are the source of failures? It's basically because of a hardware failure, some fault, some wiring connect, some circuit disconnect, something of that sort. It cannot be, we don't say that it will be definitely of the software, but it could be because of the connection or the links associated. So those were the or even the system design. So when we have defined a bad design, it might cause us failure, and then the implementation of the software. But the primary what we normally find in this industry is on hardware failure. So that's why we have this maintenance where we have to maintain the hardware of the system that we are working on as well. So maintenance of the system is very important. What could this failures impact on? Impact on health or safety. The economy might fail, and even you are losing a trustable service. So if somebody is relying on your service and you're losing their trust because of such failures. So those were the system issues. What are the software issues? Software issues, yeah, basically you have defined a certain functionality, you have implemented according to that, but you still have made some a mistake on the functionality, which is called as a functionality issue. And then what are the other software issues? Yeah, development within a time, all that is a software issue. So when we develop a software, it takes a lot of time to develop as per the specification. All these are like major issues that we face right now. So you have a functional issue, you take a lot of time to develop the software because it's critical. Then it's because of a lot of time, it cost implies. So these are the different issues. So what happened? The industry is not believing us that we will deliver an adequate software if we have these issues in our hand. So what we have, we don't meet the, what is the impact is we don't meet the delivery on time. We don't give the right software. All these are the impacts. So what is expected is on time and within budget. So that will be a failure if these are issues pertain. What are remedies for these, for the success of the software? What, like I told you initially, we have to adapt the established standards. So when we are developing every set of software, we should make sure that we are assessing, we are following the right guideline and developing it. So the standards are essential. So like I showed you in the beginning, the need of certification where you follow certain standards for each industry. Those standards have to be met. And then you have to be assessed at least, like I told you, bare minimum 3 or better. So level 5 is considered the best. So what you need to so when you say software engineering and system engineering, the remedies is basically that you need to bridge the gap between the software engineering and system engineering. How do you bridge the gap? So nothing but by leveraging the right software system engineering skills. So when I say that it's you should just not have knowledge about software, or you should just not have knowledge about system. You should have a combination. So the software system engineering skill is what would bridge the gap between these two engineering, which could be the best remedy to get a successful safety critical software. What is the future? So when I say it's important to bridge the gap between the system engineering, which can be done by leveraging the software system engineering skills. So now what we have found is something called model-based design. So when you have the knowledge of software, you have the knowledge of system. So you have a combination of both software system engineering. When you have that, it's easy for you to develop the design of the software and bring the right implementation. So we are implementing right now. We have all got into the technology where it's not just coding. So it's like we develop a model-based design. And once the design is perfectly defined, there are several ways that an auto code generator, you can generate an automatic code. So you don't have to sit and code manually. So we have got into that level where where we are building the strong model-based design. So the foundation, which is the design, we have made it model-based, wherein we define everything. All the phases of the SDLC are followed within that design, where we which comprises of the right implementation with automatic code generation. The design is you can simulate and develop the design. You can think about simulation when you are developing the design, and then you have the what all the models are given in a way, the outcomes of the model should be an executable form so that you can generate an automatic code. So all this are now done through a model-based design, which again follows a hybrid agile model where you have continuous test and verification as well. So what are the different tools that play a major role in the development of safety critical systems? So we have this domain-specific languages. So right now in aerospace, the languages that we used was ADA and C++. We haven't gone beyond that because only non-safety critical system like the flight entertainment system, like you see the in-flight entertainment system, which is your TV inside the flight. Those are all considered non-safety critical. So those have been developed using Java, Angular, JS, and stuff. But other safety critical system, which the flight pilot looks at in his cockpit display, are all considered safety critical. So for that, we had always used ADA and C++. Then automatic code generators, this is the future right now. So rather than sitting and coding, we are getting into automation world. So AI, ML, machine language, AI, all this will, machine learning and artificial intelligence will come into picture. Then we have test vector generators that also does the high level testing. It's also automatic. Then we have structural analysis. Structural analysis is nothing but to see whether the complete functional coverage is done as appropriate. Then we have configuration management. So configuration management is something, once you develop the code, you push it to a known destination or a known location where it's like a repository where you push the qualified code into, and it's a version control. So every software build that you release has to be controlled. So you have to know that the defined set of releases are in going into the proper repository. So that is all managed by the configuration management tools. Then we have certification assisting tools. Then what is VNV? It's verification and validation. So you know what is the difference between verification and validation? Whether the system is implemented right, or are we implementing the right system? So are we implementing the system right? Is the verification is when you're going through the development phase itself. So when you are on this phase, you ensure that you are going to ensure that you're going to implement the right system. So all that comes in the verification area. But validation is something once the system is built, you are going to assess whether the right system is implemented. Then we have we are going to evaluate whether in the development phase itself we are going to do. So that's what I was saying. In the very beginning, we start assessing. When we start evaluating in the very beginning from the development phase itself, that's called as verification. But when we are really almost done, that is when we do the validation of the product. So these are the different differences of so we have different points. I think these you would have there are certain activities that are included in the verification and validation. So verification is something like when you have implemented a design, you do a design review. When you have implemented the code, you do a code review. So all that is a part of verification. You have meetings, you have inspections. All that is done in the development phase itself. But in the validation phase is something like an acknowledgement. The final system is taken, you don't know the functionality, but you just blindly go and test it. That's the black box testing. You don't know the internal functionality, but just with the requirements, you go and see, you trigger inputs and see whether the system is behaving the way it has to. So all those final set of testing, that is black box, white box, gray, all this is done in the validation phase. See, so that's what. So we have to, in the verification, we normally verify whether the outputs are according to the inputs or not. But in the validation, the software is accepted only when user can accept the software only when all this is done. So the validation is something that is called like a user acceptance. Only when the user is ready to accept it, it's called that it's a validated software. Yeah. So what are the items that we evaluate in verification? There are plans, like we have the project plan, we have the verification plan, we have the software development plan. So all these plans are evaluated during the verification phase. We have even the design specification, requirement specification, code, test case. Well, like I told you, when in the V model, we go do it in parallel. So that verification happens in parallel. Even the checking of all the documents, files, everything are done in the verification phase. But in the validation, we go and check the actual product, whether the entire software is well working as per the requirement. The entire software is built as per expectation. That is validated in the validation phase. So, like I told you, it's very essential for us in the safety critical system to do this black box and white box. So, white box is something where you do when because the tester has to have a knowledge on the internal functionality. So when the implementation is done, he does unit testing, and after the unit testing and it's integrated with the hardware and everything, he does the integration testing. It's very essential part that the tester has to have a knowledge on the internal functionality when he does white box testing. But when it comes to black box testing, it's not necessary that he needs to know the internal functionality, just he has to know the system. So if the system is behaving the way it is expected or defined in the specification, he qualifies it. He said that, okay, the testing was successful. And when these two are combined, we have the gray box, where there the tester would have only a partial knowledge, would have a partial knowledge at least, not like how he has no knowledge on interfunctional functionality. He will have a knowledge, partial knowledge on the functionality. So with which he will identify the errors, and he can even suggest the developers with some design changes. So gray box testing is something like a knowledgeable tester who has the knowledge to even correct the software. So yeah, so the conclusion is basically this. So it's now one of the safety critical system software development is considered one of the evolving systems. Like it's way well developed than the earlier days. We are evolving into better systems. So we are bringing in a lot of embedded systems in our real lives. So yeah, so that is about the safety critical system. Then we are bringing in like rather than having a hardware, just a knowledge on hardware, we are working into the complexity of software and trying to bring the right aspects of the system into the software. And most what I would say, as you engineers, what I would say for your future, it's always better to focus on both system and software knowledge. It's so always it's better to be qualified as a software systems engineer than just saying that I'm just a software engineer. So having a knowledge on the system and working on the software will be bringing in the right system into the industry. So with like using appropriate automation tools, we can build the right system. So that's the conclusion. I have here some case examples. Just I wanted to show you guys on what we have worked on so far. So these are certain examples of software development that I've worked so far. So the different phases you see in the top, that what I have developed, we have a, if you see this fuel efficiency management, that is something which gives the fuel metrics in an this is for the train control. So we had this, what you're seeing is a simulator setup. So we track all the fuel metrics. We have all the data which is like based on the fuel levels, your speed, your axle, everything varies. So all these measures are viewed in this display. So these were all developed. So you can see the languages that we use to develop. So right now it's all Java centric. We are getting into Java. So you know the Java 8, Java struts. So even .NET centric. So these were the different softwares that we had, software technologies. I mean the languages that we are trying to implement in the current displays. So that was the one, and there was a driver machine interface. That is again for that was on a Windows platform, which we tried to port into a Linux platform as well. So yeah, these are the different machines or different systems that we had developed. So I've just showed you, taken some pictures to show you what how those systems look. Then we had the train control and monitoring system, which is how to control the train movement, how to the even it even takes care of the doors, brake, traction. Traction is something that forces the train to move forward. So all these systems are the all these systems we have involved in for development, and this is for the verification what we have done. So these are few examples. that we have gone through. So these are the pictures of the simulation benches that we worked on. So the brake and traction is it's kind of critical system in train, because if the brakes fail, the trains would cause an accident. So the this is considered one of a critical system, and yeah, we were involved in the hardware integration and software testing of it, even in the development, if you had seen in the previous slide. So yeah, this is the case examples, and yeah, well, thank you one and all for patiently listening to me. And yeah, it's nice addressing everyone, all the engineers over here. So if there are any questions, please you can come forward with your questions if you have any. If not, I hope I have not bored you. I have not spoiled your weekend. Hello.
So it's a Q&A session now. You can all ask your doubts and questions in the chat box or using your mic. Meanwhile, we'll share the feedback form in the chat box.
Okay. May I know who was that? I mean,
I'm Nina.
hi.
Yeah, but she from the college
Hi.
actually. Yeah, IEEE.
Oh, okay. Okay.
Yeah. Guys, any questions?
So
Please
she needs
go on.
to.
Yeah, use chat box or ask, you can ask questions.
I mean,
Hello, ma'am.
yes,
Hello. Am
you
I
can
audible?
address with your name and then, yeah,
Hello, ma'am. My name is Vivan. I'm studying mechanical engineering as a
oh,
second year student. And how much
mechanical
is the
engineer. Okay.
development of, my question is, how much is the development of quantum technologies in embedded system?
How much is the
Development of quantum technologies in embedded system.
quantum technologies? Right now, okay, I think that is more on your mechanical field. Yes, we do have we have certain engineers, mechanical engineers who work on train design, or even on the aircraft flight, what is it, door design, and certain other in aerospace industry as well. And I believe that they have used some quantum technologies as well. But I'm not much aware because I'm not from mechanical. Um, but yeah, the train design team, which the mechanical team works on, have used certain technologies. I not much aware of that. So it's more about you're talking more about the quantum computing, but we are not involved in that. It's moreover done by the train design team or train mechanical team. So yeah, but I know that we do implement certain quantum computations. Yeah. Any other questions? Still, for some it is not opening. That's what I see in the chat.
Ma'am.
Yeah. Hi, Nina.
Hi. Mohammad Nihal is asking for some resources for beginner to get started. Can you give him some options?
What he wants to what he wants?
Resources for beginners to get started.
Resources for beginners to get started. You mean pointers To get started. By the way, you are all which year of engineering you are in second or third year?
I'm currently in second year.
Second year. Okay, okay. So if it is about pointers on how to get started, if that is the question, I would say read more on domains. So it's good to have knowledge on the different domains. So it could be anything. If it's not necessary. See, I'm not an engineer, but I worked on aerospace technology. I'm in aerospace domain. And it's good to know always to open up to learn domains. And it was an interesting phase when I joined. I was also just a normal engineer, a computer science engineer who didn't have much knowledge on such domains or such criticality of the domains. I wasn't aware. So it's just when you start learning, you have to start learning on certain at one point. It's not one point, and any point learning is vast, so you shouldn't give up on that. So right now you can start learning on domains which you could find interest in. And I'm sure I should tell you that we have a lot of good scope and coming in for these industries. Like locomotive is growing vastly, because locomotive, which is nothing but train, we are bringing in a lot of technologies. We have acquired a lot of technologies from Europe, Japan, and like even US. So mostly from Europe. So right now, what you see in Kochi Metro and all, we have worked on Kochi Metro, and even in Bangalore Metro. So these are all technologies that we have acquired from European companies. So most of it, these are the so it's good to always have a learning knowledge on these systems. So I would say that start learning, pick up some topic like domain, and you can start learning from now. So you will know the system. Having a knowledge on the system is very important before you get into uh, 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 any particular stream. It's always good to know the system. So I would say start off with learning a system. We can talk about avionics, we can talk about locomotive if you want, but yeah, knowing that system is very essential. So that gives you knowledge on the system, and that knowledge will help you in developing a software for it, a built-in software for it. I know most of the guys will be more interested in learning gaming software. That's what I hear even from my own brother. So yeah, I think that would be more of interest, right?
Yeah. All right. If no
Any
more
any
question,
any other
any other
questions?
question, please? Yeah, I think if no more question, we can wind it up, I guess.
Okay.
So we have come to the end of an informative webinar. So I thank you, our speaker of today's webinar, Ms. Lisha Nair, for really edifying session, and the GCW Alumni Association Bangalore chapter, especially Mr. Arjun Sundareshan, and also Shabisa for giving us the opportunity to host the event. The event won't be complete without all of your participation. So I thank each one of you for attending this webinar. So see you all next week. Bye.
See you. See you. See you. Bye. See you next week with a different topic.
See
Bye,
you.
guys.
Thank
Good night.
you.
Thank you. Thank you so much. Bye.
Thank you. Good night.